So recording has been started. So for today's session, we'll only discuss the if you have any doubt regarding the first 3 weeks, especially first 2 weeks. Uh, Today I don't have any extra sample problems to solve for harmonic oscillator. We can do that on the next day with the solution of assignment 3. So today we'll mainly do assignment 1 and 2 we'll try to solve. If you have any specific doubts you can ask me, and then today we'll stop there. So let us wait for 2 to 3 minutes and then we can start. I think last time Avinash had a question regarding that selection rule for um, means when the psi there is 3 dimension or 2 dimension.
Yeah.
To be honest, Avinash, I didn't find any such selection rule, specific selection rule, but delta n x or delta n y related to that. But we can go ahead with that symmetric and whole wave function to be symmetrical and asymmetrical. And another question was earlier that day was due to the contour problem. So I'll start with that and then we'll go to assignment 1 and 2. Let us wait for 1 or 2 minutes, then we'll start. So Avinash, where are you from? And Arunath Pal?
I'm from Pune.
Okay. And Arunath Pal?
I'm from Kolkata.
Kolkata. Okay. So you guys are studying undergraduate degree or master degree?
No,
Uh,
yeah, please.
I have finished my graduation and I am currently working as a visiting researcher in St. Xavier's College.
Okay. Okay. So Avinash?
No, I teach.
Okay. Okay.
So I have done my PhD
So you have
uh,
already finished your PhD.
a long time ago.
Okay. Okay.
But
Great. Great.
and I have my MSc is from physical chemistry, but PhD and everything I went towards spectroscopy, and it was more of experiment. So I've forgotten everything.
So I am also currently doing PhD at IIT Bombay.
Hmm.
So I am also from physical chemistry background. Spectroscopy, I am also doing fluorescence spectroscopy and other things.
Okay.
It's nice to interact with you. So then let's start then. I think other let's see whoever will join will join. So do you guys had any doubt regarding the contour diagram or
No.
no, right? Arunapal, should I?
I have one doubt regarding
Okay,
Hermite polynomials and the recursion
okay,
rule that we had done in the week
okay,
3.
okay. So I don't remember means I don't recall the rule. But you can ask me. Let's see if I can give you the answer.
My doubt is like we derived the recursion formula first, and from there we arrived at the conclusion that we either have all odd coefficients or all
Hmm.
even coefficients.
Hmm.
And from there we went to Hermite polynomials.
Yes.
So if we know the Hermite polynomials now, so
Hmm.
during solving any problem, do we again need to refer back to the recursion formula, or just knowing the Hermite polynomials would be sufficient?
I think knowing the Hermite polynomial should be sufficient because if you know the Hermite polynomial of n is equal to 1, then already I think another recursion formula is there which will relate to you n is equal to 2 and n is equal to 0 like that. Or do you get my point?
Yeah, the
So
recursion formula for the Hermite polynomials.
okay, so I don't exactly remember the formula, but let's see what was that. I had the actually uh, the slides. So this is for tunneling. So let me check. Um, maybe here. Acha, you can't see my screen right now, no? I have not shared it.
No.
Okay, so let me find that out and I'll share the same with you. Currently, I'm finding the equation. Yeah, so let me share the screen. So you guys can see my screen right now, right?
Yes.
I think you were talking about this recursion formula. If I get a, let me go step by step.
Yeah, we derived the recursion formula, and from
Yes,
there we concluded that we either
only,
have odd or even.
yeah. So suppose let me write here. You can understand that when a actually we have come to the why we have come to the conclusion because that these Hermite series or this series should end. This can't be a infinite series because if you see the solution of this, let me get back to some of the previous slides. Do you have them? Yeah. So you see this general solution, right? So if this b, we took this b as 0, coefficient of b, or else this psi would have blown up. Then it would not have been normalizable. Similarly, if this Hermite polynomial would have been infinite series, then it would have been blown up. That's why we need to stop at a certain point, and it will stop it by itself by the recursion formula itself when j equals to v max, right? Or j equals to v here.
Yeah.
So a of a plus 2 will be 0, and similarly the series will stop here. So that means a j plus 3 is 0, right? And whatever
Yes.
a j plus 4 will be again 0, means the series is stopped. Now, uh, a of aj is not 0, but you will see as aj plus 3 is 0. Let me write it like that: aj plus 3. If this should have been the case, then this should have been j plus 1 minus v by j plus 1 plus 1, j plus 1 plus 2, aj plus 1. So if this is 0, then aj plus 1 is also 0. Like that, all the odd terms are 0 now.
Yes.
Odd terms are 0.
Actually,
And
I have a question here.
yes,
Like because you are saying aj plus 3 is 0, so
yes,
therefore aj plus 1 is 0.
yes.
Now, can we
Because this term is not 0 anymore. I also had that doubt.
uh, so
If this term was 0, because j equals to v, we are getting aj plus 3 is 0, right?
mhm,
So if j equals to v, then still the 2 is there, right?
mhm,
So this term is not 0.
okay.
So aj plus 1 will be 0. And like that, all the odd terms will be 0. So we'll when for this particular situation, we'll get all the means there will only be the even terms, and when we'll start from the odd, there will only be the odd terms, like that.
No, no, I still now we are going down like from aj plus 3 is 0, so aj plus 1 is 0. Aj plus 1 anyway would be 0 because your J max is V.
Yes.
But can we extrapolate it saying that since AJ plus 1 is 0,
Hmm.
AJ minus 1 is 0?
AJ minus 1.
Mhm.
Because see, the J is here integer, right?
Yeah.
So if we go back, suppose this is 5, then not 5, suppose J is even here, right? J is even, that's why we are getting only the odd terms here 0. So
Mhm.
suppose for this J, if J equals to uh, 2, then we are saying that uh, A5 is 0 and A3 is 0.
Mhm.
So that's why we are saying that A1 will be also be 0. Are we extrapolating that too much? You are thinking, you can tell me if.
Because now if you rewrite this equation, A3
Hmm,
will be equal to, right?
hmm.
A3 will be equal to, now it will be 2 times 2 minus 2. So that will be 0.
Suppose this is A3.
So J is equal to 1, which means, right?
So J equals to 1. J equals to 1. 1
Mhm.
plus 1. And we already took that J will be equals to V. So it
Mhm.
is 1.
Mhm.
So, and all the things here 3 into 4. And here we have 1. So if
So
we already got A3 0, then here 1 plus 1, 2 minus 1, 1.
so this is non-zero, so A1 has to be 0.
A1 has to be 0, right?
Mhm.
So by that way, we are going down this order so
Mhm.
that uh, this could have been possible.
But by the same logic, let's say if now we are saying that J max is 0. J max is not 0, right?
Um, J max is not 0. I have done some mistake here. I think the J is 1. Yes, yes, tell me.
No, suppose so. What you are saying is uh, J plus 3 is 0, so J plus 1 is 0, correct?
Hmm, hmm. When we are choosing for a such a J max is equal to V. So
But by the same
when that
logic,
J max is even, we have to understand when the J max is, I think, even should have been, right? Then the odd terms will be 0. So this is a little bit confusing. I know. When I first saw this lecture, means then also I went to when actually Datta sir is my supervisor, so I went back to him, and so I also cleared my doubt like that. Yes, yes, yes. Is anyone asking any doubts? I can't hear actually. Can you repeat?
no, I don't think so.
Okay. So like that means only odd and only even terms will be there for a means Hermite polynomials for this case, and that would lead to another recursion formula that if we know the nu is equal to 1, then we can go for 3 and 0 like that, and that's how we'll get our all these uh, formulas. Actually, if this H nu, this would not it if it would have been a infinite series, then it would have contained a term like this epsilon square. So the whole term would have been e to the power minus this is xi square. So this would have been something like e to the power uh, xi square by 2. So this would not have been a normalizable, not normalizable, because it is blown up, right? At infinity, plus minus infinity. That's why the series has to end, and that's why that at particular that recursion formula you will see that only odd terms are there or even terms are Okay. So, any other doubts? Or we can go to directly to the assignment questions, and uh, we don't have to solve all the question because these are pretty easy, I guess.
Mhm.
So, if anyone had any specific doubt, we can solve that.
Can you go down?
Yes.
No, you. There was somewhere. Yeah, this question number 9.
Question number 9.
Mhm.
Yes. Among the following, the statements which is or are not among the postulates of quantum mechanics is or are central
Okay.
localization of mass and positive charge. That is given by, I think, Rutherford, right?
Mm-hmm.
Okay. Circular orbits is also given by, not
Bohr.
really given by Rutherford, but Bohr.
Yeah.
Bohr took it from, actually not directly from quantum mechanics, was not, he did not use quantum mechanics, but he used both the things from
Mm.
classical mechanics and
Yeah.
from uh,
Bit of this and bit of that.
bit of this.
Mm.
And what is next? Electrostatic attraction between nucleus and proton. This is again given by Rutherford. Continuous emission of radiation by an atom due to electronic transition. That is also
Bohr.
continuous emission.
Sure.
That,
This
then
is
continuous.
Rutherford.
This is also Rutherford. Among the following, the statements which is or are not among the postulates.
So all of them should
Circular.
be.
Actually, the circular thing will come. Uh,
No, quantum mechanics will not have orbits. It talks in terms of probabilistic, so it will go to
Probabilistic. Yes, you're right. Yes.
orbitals. It will go.
Okay. Yeah.
There are no orbits in quantum mechanics.
Sure. Sure. Central localization of mass and positive charge would have been a wrong answer because it is given by Rutherford. Electrostatic attraction between nucleus and electron was also not given, I guess. Continuous emission of radiation by an atom due to electronic transition. Actually, continuous emission is the term which I am not getting. Continuous emission given uh, mm, by
I
the
think
Rutherford formula, but
over here,
That
I
is
don't think.
given by Maxwell, no?
yeah,
Maxwell.
yes. But that is when it is an accelerated particle. So it is here written that by an atom due to electronic transition, and electronic transition was discussed in Bohr's model.
Anyway, it is not a postulate because the postulate of quantum
Yes,
mechanics
none of
nowhere
them are.
Mm,
it
mm,
says that.
true. So what was the answer? So means what answer means which is or are. So we are getting
I
into point
think,
that all four are not
yeah,
related to
because
the
in
postulate of
the
quantum.
corrected assignment, I think 1 and 3 is the option.
1 and 3. This central localization and electrostatic assay are wrong, but circular orbits and this continuous emission was given right. Okay, I'll check
Yeah,
that. I'll check that.
because circular orbits cannot be there in quantum mechanics.
I'll check that. Yes. Okay. Nice. Question number 9. Okay. Do you have any such doubts in any other questions?
Not in assignment 1.
Okay. So actually, I had one doubt here
Mm-hmm.
because this one of this following wave function, acceptable wave function.
Mm-hmm.
Today I have just corrected the answer. What will be the answer of the following? Which will be the acceptable wave function?
First is acceptable.
Okay, that we have already once
Yes.
tried.
Then
The
yes.
second one,
Then D is acceptable
V is acceptable
because it's a Gaussian.
at x is equal to infinity. B or D? B or D?
D
D,
for Delhi.
D is acceptable. I heard B. Okay.
Yeah.
And what
D is
about
a
C?
Gaussian.
Yeah. And what about C?
For C, we would have multiple values for the same x.
Yeah. Actually, I also had the same doubt. But the thing is, when there will be given sine inverse x, actually, if we go back to the 11-12 books, then it was clearly written the domain and those things are there. It was clearly written it is actually the sine inverse x is valid inside this boundary. Only that this is 0. Oh, means let me the actually it will look like this. So and here the values are suppose so y-axis is sine inverse x
Mhm.
and this is x. So actually at this value, I think this is 0 pi by sorry, I'm making a mistake. So for values of pi by 2, x is when pi by 2, then it would have been 1 comma 0, and when it is minus pi by 2 x, it is minus pi by 2, it is
Uh,
minus.
isn't this labeling going opposite? Like in the on the x-axis, we should have 1 and -1 as our boundaries, and
No, no,
on the
no.
y.
No, it should be pi
uh,
by 2. I think that's correct.
at x
Because
is equal to pi by 2 only, I
this,
think
this is the
sine
angle.
inverse. Yes, x is now angle, right?
Yeah.
Yes. So
We
actually,
are plotting inverse, right?
yes, we are plotting inwards.
Yeah, so x should be the value.
No, the here y means this is our dependable. Now x is suppose
Independent.
x is independent, right?
Hmm.
So
Yeah, so we are putting that inside sine inverse. So how can that cross ±1 boundary?
so suppose as x is equal to pi by 2, what will be the value? Oh, I have made mistake. Sin in x would be 1. Yes, yes, you're correct. You're correct. We have made mistakes. So x should have been 1, comma 1 at x is equal. Sorry, let me draw it properly. Okay. Actually, there was discussion for this question also. Actually, we generally write it that it is not a acceptable wave function, thinking that it is multiple regions are actually there, but actually the sine inverse x is valid inside this boundary. When x is equal to 1, then it is pi by 2, right? And this is minus pi by 2. You can check that in some graphical form, means if you want to draw the graphs also. So actually, you will see that it is this function is normalizable within this boundary. It is not infinite because it is finite. It means this just ends here. This doesn't go beyond this for sine inverse x. If nothing is written then. So actually, this will
Just
also be
a
a
question. Suppose
yes.
if y is equal to sine inverse x.
Y is equal to sine inverse x. Yes, yes, yeah. Y
Uh,
is
my question is now I'm not. This is a very basic question. I just don't understand. Can we write x is equal to sine y?
x is equal to sine not for all the values we can't actually. For the actually with sine inverse x there is this problem. For
Uh,
mathematical background I also don't know. That's why
yeah,
I
but
told already
again,
that.
this question that when you say x is equal to 1,
Hmm.
sine inverse x is pi by 2.
Yes,
But it can be 5 pi by 2 also.
5 pi by 2 also we can argue that at 3 pi it will again some pi it will again be 0, right?
Yes, yes.
That's what I I also thought when we solved, I think means you were not there. Actually, we were solving week 0 as our demo run. That time also we tried to solve this. That time I solved it as that it would not have been an acceptable wave function because of that it is not never ending. Means it's infinitely long. But when I discussed with Professor
So in
Datta,
fact,
actually,
not
yes.
just infinity, it will not be single valued.
It will not, yes, but yes, that's what have been the problem, right? If it goes like this again, so at for this x you would have got two values, but the main problem is that what I understood, I don't know the exact mathematical background of this, but the thing is that sine inverse x would not be valid over this boundary y is equal to pi by 2 comma 0 and here 1 1 2 minus 1 for x. We need to check this question again. If I got some valid reasoning why this is bound between these things, then I would like to then uh, actually I already asked whoever the TA is. TA means associated with that NPTEL assignments. I told him to correct actually this answer. So actually sine inverse x would have been also a correct answer. So if you get any material, please give me. I will also check for this. Actually, 11, 12 mathematics also I also forgot. I'm very sorry for that. Do anyone else can contribute here? That what should have been the boundary for sine inverse x? Anyone else have any input? I also thought because of that, as it is not a single valuedness, because of that it would have been a non unacceptable wave function. But actually, this is not. Uh, it is a bound wave function. Means it would not have been exist over that boundary. So that single valuedness question would not have been. Okay, so we'll discuss this question again in the next time, I guess. So question number 9 and question number 12. Now assignment 2. So first three are easy, I guess. Question number 2, you have to check the how many nodes are there. According to that, energy will be calculated. Well, not you don't have to calculate. The more the nodes, more the energy. So what will be the answer? Can anyone tell me? A quantum particle in one dimension X moves under the influence of a potential that suppose bound states. Plotted below are the wave functions. Identify the wave functions corresponding to the ground state, means the and the
Ground state
highest energy.
will not have any node,
Yes.
so that will be
Option
4.
C.
Uh, no, at nodes, what happens? What is the definition of a node? Again, we have to go to the basic.
Sign changes.
Sign changes.
Yes, sign
And
of the
size
psi
0.
change.
Size
Psi
0.
is 0 and sign of the psi changes. Both the things.
And size changes, yes.
Yes. So as you can see, I think for 4, how many nodes are there?
No nodes.
No nodes. For 3,
2.
2. For the 2, I think 1,
There are
2, 3.
3. 1, 2,
More
3, 4, 4 nodes.
1, 2, 3, 4, 5, 5.
4 nodes. No, 4.
1, 2, 3, 4, 5. Right?
Yeah, 5.
5.
Hmm.
And what about the 1? That is 1 node. Only
1
1.
node. Yeah,
And here are 2 nodes. And
2
here 0
nodes.
nodes. So
Hmm.
as we already know that more the nodes, more the energy.
Hmm.
So that's why this is the highest energy and this is high.
Hmm.
You don't have to calculate anything. The question is itself so big that anyone will think it is a very hard question.
For
So
this question number 1,
okay, Yes.
Second is the correct answer because for a free particle, you cannot, it's not integrable.
Yes.
But what about this fourth one? The average momentum is zero.
Average momentum is zero.
Uh-huh.
So the free particle, what is the equation? Psi is equal to
Psi
A.
is equal to
Can
A
anyone help?
sine kx plus b
Is
cos
it
kx.
sine or e to the power? Means we can write it anyway.
Yeah.
Can we write it in? If we go through this, then this I think that momentum thing will be easily achievable because that I term is there. No?
Hmm.
I don't actually remember. Can anyone help me? What is the? Uh, let me check then. I have presentation. Then let's see. I also don't remember that.
It will be on the first of, yeah, over there. No, yeah,
Particle.
yeah,
Yeah.
yeah.
Enigmatic function.
Hmm.
Free particle. A sin x plus cos x trial solution. With that only we could have
Hmm. Hmm.
go. Okay. So energy, there is no bound to energy as we already the
Yeah.
first
Uh,
question, and
hmm.
that is,
Uh,
let me see then, uh, a sin x, a sin kx plus b cos x.
it is after this again. It will be written. Just go ahead.
Achha,
Little bit.
okay, I should not write here. Process. Okay, this thing you are saying,
Yeah,
the final thing, na?
yeah. This is the final. Yeah.
Okay, okay. So there are no restriction of k. That's why it can have any energy. Psi of x, then we have to see that if it is an it would not, let us see if it's a eigenfunction of p of x or not. So let me write it in mind.
Because during the lecture,
Hmm.
uh, he said that this k value,
Yes.
k is plus minus of square root of 2 me by h
Hmm.
cross.
Hmm.
Uh, this actually represents the momentum,
Yes.
and plus minus just gives you the direction.
Yes.
Plus is on one side, and so minus
When
is
he
on.
discussed that particle in a box model, right? That
No,
why the
yeah,
average momentum of a
yeah,
particle in a box will be
yeah,
zero,
zero.
right?
Yes.
Yes.
So because if you have plus minus here also,
Hmm.
and if k represents the momentum, why should that also be zero?
K doesn't, acha,
Yes, he
means
says.
the value, eigenvalue you're saying. Okay.
Yes, he says k represents the momentum of the particle, free particle.
Hmm. I have to check also that.
Because of course, the easy way and the correct way would be we can find out the expectation of p.
Hmm. Can we
But
do that really?
but the problem is we don't know the values of a and b.
Because it is not normalizable again,
Yeah, yeah,
coming to the point. Then
uh,
how can we get,
yeah,
where is the question? Yes. Then how can we get the average momentum
yes,
or expectation value? Right.
yes,
So we will not get the average momentum because it is not normalizable. The first
mhm,
point.
yeah,
So again, so it is, means average momentum is not zero because we can't actually really calculate for this uh, this free particle when we think like, suppose in a box, sir, I think professor told, right, that in reality there is nothing such as infinity, only 10 nanometer or 1 feet distance itself for a small atom or molecule would have been an infinity, right?
yeah,
So box normalization is the thing what we generally do for free particle to normalize it. I
yes.
also don't know. It's very, there is a very tricky derivation is also there. I don't want to go to that because I also don't know, to be very honest. But here, so the average momentum is zero because we can't really, it's not zero because we can't do that, and a velocity of
No,
zero is
see,
not allowed. Yes.
you cannot find out is a different thing.
Yeah.
Saying that D is not an option is a different thing.
Average momentum is 0 means you are saying that we can't define. Actually, it
We
is
cannot,
indefined, right?
yeah, we cannot find it by the that expectation
Value,
formula.
formula of the expectation value. Yes.
But it just means we cannot calculate.
Mm,
And because if your K value is both plus and minus,
hmm.
plus and minus means
On
one.
both
Uh,
to other directions, means
yeah.
opposite direction.
So by common
Yes.
sense, if you just see the average, average should be 0.
Should have been, yes.
Of course, we cannot confirm it by a formula like we do in particle in one box.
Hmm.
In particle in one box, we can calculate because we know the boundary conditions.
Yes. Here we don't have the boundary. Yes.
Here we cannot integrate it. But
Yes.
forget the integration part because your K value has both plus and minus value from the origin wherever we define the origin as.
Hmm.
So the average should be 0. Don't you think so? I don't know.
Average should have been 0 if you compare it with that previous example of that particle in a box. But again,
Yeah, particle
uh,
in a box actually, if you forget the math part, the
hmm.
logic is that
Yeah, logic is that the
logic is
directions are
yeah,
different.
yeah, it moves in
Velocity,
both the directions, so it should be
yes,
0.
yes,
Just because you don't have the boundary condition on the outside, inside
hmm,
is the same story,
yes,
or even for a free particle.
true.
So I don't know. I just thought that this also should be 0.
Hmm. I'll check. I'll check if some better answers are there or not. Uh, I will come back to on this also. Okay.
Okay.
Any other questions? Quantum number of a particle of a box arises out of the boundary condition single valued, right? So
This
then,
also I don't understand actually.
yes. Tell me.
See this one.
The third question, right?
Yes.
So quantum numbers of a particle of a box arises out of requirement of the following. So in Schrodinger equation, when we are starting, there is no such. We are not giving any. Are we giving anything? Any quantum number psi n or any other? Are we providing it,
No,
or
there's no
just we are
quantization.
writing psi?
There's no
Right.
quantization. Yes.
Yes. So when suppose for particle in a box, here particle in a box is only given. So
Mhm.
when the boundary conditions are there, right? That
Mhm.
let me draw it. Sorry, x is equal to 0 and x is equal to L. So as we already know, this is like that, or this is n is equal to 1.
Ground state. Yeah.
Yeah. So this is n equals to 2. So this is I'm plotting psi only.
Mhm.
Psi of n. This is n is equal to 2.
2.
So from here only that boundary condition. Here my psi is 0 here.
Mhm.
Is not means yes, psi is 0 because V is infinite, potential is infinite.
Yeah.
So that's why that when these boundary conditions come, then that K value was there, right?
Mhm.
That has a
That becomes
then
quantized.
yes, particle become
But my
quantized.
question is,
Yes,
the reason for this boundary condition is not because of single valued. It should be because of normalizability.
continuous
Norm-
also.
No, normalizability. Because see, the reason why we went from free particle to a particle in a box was that in a free particle, every other it was continuous,
Hmm.
it was single valued, but
Hmm.
we could not integrate it over the entire space to get a value of 1.
I didn't get it. Can you repeat?
Okay, yeah. See, we first discussed this question of free particle.
Yes, the
In
previous
free
video.
particle, there is no quantization,
Yes,
but that
because
is
there
not
is no boundary. Because there is
no.
no
But
boundary.
quantization is not our aim to begin with. we just want a psi, and we'll see, like whatever comes
Yes,
from that, it will come on its own.
yes, yes,
But the problem was that the psi that we get for with particle free particle, we could not normalize it
yes.
because it was not integrable.
Hmm.
So
Because psi is we cannot really go to the real psi, means the actual what is psi or normalized constant. We can't really go to there.
yes, so to overcome that problem, we use this concept of box.
We are means box normalization means we
Yes,
are
we
just
put in a
putting this
box.
in a box. Yeah.
So I thought that the reason why we went from particle in a like free particle to a particle in one box is the problem of normalizability.
Hmm.
Because if you say single valued is there in free particle also. Even
Okay.
continuity, there's no problem in free particle also.
Hmm. So
Uh, my I thought that the answer should be one.
that is one of the answer. Someone can also argue the continuous should be also another thing, right? Because
No, free
at
particle psi
boundary
is continuous.
psi is continuous, right?
Yes, phi is single valued. It is continuous.
Yeah. Means here
It
it
was
will
the
be
only problem was it was not integrable.
yeah.
So to make it integrable, and in free particle we don't have the quantization. It doesn't
Actually, I
arise.
think the question is I think framed wrong. This is not for a particle in a box, right? The question is really from I think the question is wrong. Particle in a not for a particle in a box. This should be in a question for rigid rotor. If you go to week 5, I think it is on week 5 or week 4. I don't remember.
Because as such, I think the answer should be
Yes,
one.
actually for spherical harmonics that thing actually comes up. What I remember because that single valuedness. Here that single valuedness thing should not be the
Because
answer.
if you take a free particle, it is
The
single value.
answer given is single valued, right? Or
Yeah,
continuous or
yeah.
normalized.
One of two and three. I think the answer should be one actually.
I think this is a only MCQ. I think only one answer is correct.
Only one answer. I had ticked one
Okay, so that
and
is
wrong,
wrong.
and answer was
And
given was two or three. But I think two or
two or
three
three.
are both are wrong answers.
I can bid for
The
three because
question could have been framed based on the general discussion that we had at the beginning of the course, like where Sir told us like how quantization arrived in Schrodinger's treatment. There it
yes.
was discussed that from boundary conditions the quantum
Hmm.
numbers came. So I
Mhm.
think
Hmm.
in that sense they picked continuous as the correct answer because that was our boundary condition.
No,
Okay.
the reason why we would put boundary condition is not the problem of continuity. It was the problem of normalizability. And as soon as you put those boundary conditions, quantum numbers pops out on its own.
Actually, that free particle is what you are saying that is only to the free particle. Actually, the free particle problem is solved some otherwise also. I don't really go into that because I also don't know. But the problem you are mentioning with about the box normalization, because how can we normalize it in a means if we put it inside a box, then the boundary condition is coming because we wanted to normalize it.
Correct.
That is your question, Avinash.
Yes.
And another point, the single valued cannot be the answer. What I guess from here because that is for a different question. That is not for a particle in a box. Um, it should be single valued. The wave function should be single valued. That is a different thing to be acceptable.
Mhm.
Uh, but I want to bait for continuous actually. I am not also sure that normalizable will be answer because um, normalizable it should be normalizable to be a valid wave function. But is it really a requirement? Means it comes out of the requirement that
Because as
because already for particles, suppose we are not going towards that free particle, only we are given with the particle in a box system.
but
So
see,
already
we have
given that
done this. This is assignment two, and
assignment 2. Yes.
So this question should be based on week 1 and week 2.
Yes. Yes.
In week 1 and week 2, all we have done is particle in a
They are in a
box.
box. Particle in
Yes.
a box and free particle a little bit. Yes.
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 So we cannot take in some other concept, and for this question in assignment 2, that cannot be a valid answer.
We can go for, I think, both the answer, right? Normalizable and continuous. What do you think?
As far as I remember, I think free particle was continuous also.
Uh, Free particle was continuous.
Yes, it was
All
single.
because no, it has to be continuous. Suppose, see,
Yes,
it has to be continuous to
yes,
be
it
a.
was single value. So the
So
very
all the
reason
things, but
why we went from free particle to a box was that
hmm,
we could not normalize it.
yes, that's a valid
I don't know.
point actually. Yeah, that's a valid point. But when we are solving the thing, right? So when we are solving the equation,
Mhm.
then what is coming? Means here, suppose we are getting psi is equal to similar a sine
Kx
kx
plus b
plus b cos
cos
a,
kx.
right?
Yeah.
So now the bound, suppose there are boundary condition. What is the boundary condition? Here it is 0, at
Mhm.
just here the psi is 0, and at the boundary it should have been 0. So at psi is equal to x is equal to 0, what we call a into 0 plus b into 1, right?
So b becomes 0.
So b becomes 0. So psi is equal to a sine k.
Yeah, that's what we do in particle in 1D.
Yes. So from the boundary condition, it is coming that a is there. So the normalizability will also come because now a is there, and you are saying that from the free particle, as we could not have been normalized that in without the boundary, so the boundary are means the boundaries are here. Now we can normalize it, and that's why it should have
And
been the
once you
answer.
put the boundary condition, quantum numbers
Hmm.
come automatically out of it.
And because it is coming from the boundary conditions
Yeah,
only.
yeah.
Good point. Okay. I think we need to change the answer for these questions also. Question number 3. Great discussion actually. So I need to discuss these assignment questions more. I thought the questions are, I mean, the answers are all okay for the questions. Okay, so there is a problem also. But the continuity will also be an answer. So this is, I think, a MSQ type answer, because if you see this psi at x equal to 0 is 0 because of that continuous factor, because here also x is equal to outside the box, it is 0, right?
Mhm.
So the continuous should have been also an answer, both normalizable and continuous. Okay, I'll check with professor. Okay. And anyone have any other input to this question? Any other inputs? Okay then. So let us go to the next page then. With 4, 5, and 6. Avinash, do you have anything here?
No, that's not what.
No, right? Ila, I guess Ila was there. Saint Xavier's, I forgot the name. It's a little bit tough name. Who are you again? Yes, some Devnath. Um,
Yeah, I was
yeah, what was the name? What is your name?
Aruna Paul.
Arunath. Yes, yes. Do you have any doubts in any other questions?
No, regarding the assignment, I don't have any more.
Okay. So, do you want to give any input to this previous question? This question number 3. What do you think that should we go for 2 answers, or Avinash is correct that normalizable is the only thing?
I actually didn't think about the normalization. I remembered that while we derived the uh,
Hmm.
box in a particle problem, I remembered that we used that the continuity should be implied because of Born interpretation, and
Yes,
from there we implied the b equal to 0, and then quantized the thing. That's
but
why I went with continuity.
Bond interpretation also means tells us about the normalizability, right?
Yeah,
Hmm. So we have to check that question seriously. Yes.
I didn't think about
I also didn't think.
normalizability at all.
That's the good thing coming out of this interactive session, right? I also come to know. I also didn't think about that. Great. Thank you, Avinash. So let us go then. If anyone else, do you have any doubts in this question? Question number 4, 5, 6? Or should I just go to the next ones? Okay. Question number 7 and 8. 7 and 8. Mathematics. A little mathematics is there. Any doubt in solving this question? 7 and 8. Till 7 to you will easily do. What about the 8? Uh, was it means what is the degeneration means? Is it actually degenerate or
It's
non-degenerate?
non-degenerate.
Okay, Avinash to give his answer, and I want other answers also. Achha, you guys already know the answer, na? Others also already know. Yes, it should be a non-degenerate because the lengths are different. Yeah, if the lengths would have been same,
Hmm.
then it would have been uh, threefold degenerate, right?
Yeah.
1 2 2 2 1 1
Yeah. Hmm.
and 1 2 1. Yes. Okay. For assignments, acha, another question is this is also I think discussed in the lecture, right?
It is there.
Yeah. So this is a wave function of a wave packet actually. So I think you have got the answer. There are sum of cosine functions. If it would given as a sum of sine functions, also the correct answer it would have been, and it is a sum of exponential function too. Uh,
Actually, the sum of exponential function, I clicked that option and it showed wrong.
okay, should not have been the case.
Oh, actually, I think no. In my case, it showed wrong because I clicked it as eigenfunction of linear momentum vector as well. I
No,
clicked
no,
3
Same.
options. That's why.
no, no,
I
no.
Sorry.
clicked 1 and 2. I think 1 and 2 is
Yeah,
right.
yeah, yes.
I
Then
clicked
I
the
think
4 ones.
partial. I think then yeah, for partial wrong or partial correct, they didn't give any mark. Okay,
Yeah.
okay. So the quantum
But
mechanical
anyway,
tunnel.
there are
Yeah,
more than one answers. We should
yes.
get partial marks also, I think.
And that's why they didn't give you. You can click all 4 right and get one. Suppose two of the answers are correct. You click all 4.
Okay.
So 2 are correct anyway, right?
Yeah. If one is wrong, it gives 0.
That's why I guess that's why it is like that. So the last question is quantum mechanical tunneling is favored when the energy barrier is what? So I don't remember actually the equation, but I just know what will be the
He
answer
says,
because
says that it should be higher and narrower.
yeah, yeah,
If you just think of a wall, forget
just
all the
logically, yeah,
equations. Yeah.
yeah. What you can't get from the logic because the mass of that particle. What should be the mass, higher or lower for better tunneling?
Yeah. If it is bulky, it won't be able to tunnel.
Yes. So the mass should
That's
also be
also
less.
logical only. Means without,
Logically, yeah, yeah.
if
You
you have a
don't have
big
to
thing,
go to
it
the
is
equation.
very difficult to get
Very
through.
complicated, very complicated.
Yeah.
And you were already studying that week 3 harmonic oscillator question, right? Harmonic oscillator lecture. So there also I think open question was there, that why the wave functions are outside that
Yeah. Yes. Yes.
outside. It is because that it is a finite.
It's not
Uh,
infinite.
yeah, it's not infinite the potential, because it is finite. That's why
Hmm.
some of that is going out. And if you see that when the number of n, that n or v here, it will increase, the probability of staying inside, means it will, Bohr correspondence theory, it is known as Bohr corresponding theory,
Mhm.
that
It tends to classical.
it tends to the classical picture.
Yeah.
So in classically you can't throw a ball through a wall, right? And
Hmm.
ball cannot go outside. Similarly like that. So
So the probability of tunneling becomes less when we go to higher quantum number.
yes,
Okay.
because it is going to the classical picture, right? So that's, so I don't have any more question. You guys can shoot me question. I am
Actually, I have some more doubt about that Hermite polynomial and uh,
yes. Okay.
solving the for wave functions.
Okay.
The wave functions, like the expression we had, like psi is equal to nv times Hermite polynomial times the Gaussian function.
Yes.
So the
Let me
nv,
let me go to that particular
yeah,
slide
yeah.
then. I think I should not write here. Yeah. Where are we
After
talking about?
after this slide,
Okay. Yeah.
yeah.
Hmm.
Now, to find the wave functions, we should multiply the Gaussian with the corresponding Hermite polynomial, and there was a constant nv.
Hmm.
So that constant nv is for normalization.
Constant NV, where can you show me?
I think after this, is there a slide? There was a yeah, this slide.
That is for normalization constant.
Okay, so now suppose
Sorry.
yeah, we suppose start from a particular psi. Suppose
Hmm.
psi 4. We are starting from psi 4.
Hmm.
Now we know the Hermite polynomial H4 psi.
H4. Yes.
Uh, Now if I want to find the other wave functions above 4 or below 4, uh,
Hmm.
from that, is there any way to find it? I was having doubt about that recursion formula while we are using.
Recursion formula actually relates that both the, I think it will relate, but I don't think you can get the, suppose you get you have psi 4, I don't think you will get psi 3 or psi 1. Is psi
Yeah,
2
I think the NV I couldn't calculate. I was having
yes,
that doubt.
yes.
Like,
That I think you can do with the ladder operator, right?
yeah, I mean, so if I want to know other wave functions, then I have to use the ladder operator.
Yes, yes.
Okay.
Actually, during the means I haven't actually, to be honest, I haven't done this part of harmonic oscillator.
Okay,
But Professor Datta, when he started this recursion formula,
okay.
before that he did the ladder formula
Yes,
operators, and he said that in ladder operator you can find out the energies and wave functions of one
yes,
up or one down according
yes,
by using your a plus or a minus.
yes.
Then he says, but in that case, you have to do this calculation over and over again for each case.
Actually, a normalization constant will come. Suppose you will get the energy, but the exact wave function will have a normalization term. That is also can be you can calculate actually.
And he
Uh,
said that to overcome this situation where you have to work individual case, we go to a formula called recursion formula where we have a common general equation whereby we can get from one wave function to another wave function very easily.
Okay.
That's what he said, and I don't
Yeah,
know like how it eventually comes out to be. I don't know that part, but this is what he had said. The reason why we went to recursion formula.
maybe that.
Actually, this is why I was getting confused too. Like, I was
Okay.
trying to relate two shis, mani suppose shy 4 and shy 2, I was trying to relate them. But the recursion formula is relating the coefficients of one wave function for a fixed v, right?
Yes. Yeah, you can let me go to that particular slide. What you here? I see. Yeah, right. The Harmonic
Yeah,
polynomials.
yeah, here.
So mean, what I was trying to then solve, I found that like if we know the Hermite polynomials, then we can multiply that with Gaussian, and
Gaussian.
then we need to do the
Normalize that.
normalization, right?
Yes. Yes. So you just have to. You don't have to know early. You don't have to have earlier notion of that normalization constant. You just do the integration, and you can. I think you will get to that particular wave function, right?
Yeah, and I was trying to calculate like if I don't know the Hermitian coefficients, then those coefficients I can calculate from this recursion formula.
Aj plus 2 is equal to 2j plus 1
Yeah,
minus 2.
like
Yes.
when we have a fixed v,
Yeah.
Mhm.
is there any problem, or can you refer to any book where I can find any example? I was looking in Griffith's book, but there was no such example.
I actually didn't look for that in this week actually. So
Oh,
I will see, I'll check, and if I have some, I get some problem, I'll share in the discussion forum.
yeah, please share that. And
Okay.
just any example if there is any.
Okay. Okay. Yes. Any other doubts? So there are a lot of, I think, going to be questions which are required to be changed. I think answer in assignments. I'll check that. Check that. If there is any update, you will get. I think if I will discuss with professor. If he has some other uh, explanation, then I will also share with you. With you guys. Okay. So what is
Okay.
the time today? Oh, 7:02. Any other doubts you can share? So how to right now week 3 lectures are going on only, or week 4 has already you have started.
And three only.
Week 3
Yeah, I
only.
have started week 4.
Okay, so you got it through YouTube.
No,
No, week 4
it's
is
there.
uploaded.
Week 4 is
Oh,
there. It's
week
uploaded.
4 is okay.
I just haven't started.
Okay. No, you can. I think week 4 is given, na? So I have to check for the week 5 assignments also. Okay, I have to read week 5 also. Actually, the quantum is such a vast thing na, that I have to read means many times. If I have to teach or if I have to interact with you guys after 1 year, na, I also have to read this thing. And every time you will read, a new thing will come up. The quantum is really, it's not tough, it's good actually if you do these things. So today was a great learning experience. There are a lot of errors actually. I also didn't think about this problem, right? Okay. Okay then. So if you don't have any question, then we can stop today's session.
Yeah. Okay.
Okay.
Thank you for joining.